Thank you very much indeed, everyone. I was asked today to give you a talk about astronomy and education and where do we go next. I think the important thing to bear in mind is that science is a key bit that underpins astronomy. So when you're looking at where do you go to with education next, you need to look at the science education and within that, astronomy education. And looking at how things have progressed up until now, as with so many things, you've got a past that informs the present, and the present will inform the future, but there are two futures and you need to choose which one you want. The present will predict a likely future, and you hope it's the desired future, but they are not necessarily the same. So you need to bear that in mind. One of the things that I have been really aware of as I have been teaching astronomy and science is there does seem to be a focus on facts being good, and therefore more facts are better, and more facts done more efficiently is better still, but it can lead to a problem. The problem is, where's the time to think? Where's the time to reflect? Where's the time to understand? And the assumption almost is, well, thinking is good provided it's efficient, but sometimes thinking can't be programmed like that. Thinking needs time to evaluate and understand. And it's almost when you're looking to the future, you have to bear in mind that some would say, well, the best thing to do is to have 20/20 hindsight, provided you sort it out in advance. And that doesn't always work. We've also got an advantage of new technology and the disadvantage that goes with it, and quite a lot of people don't seem to understand the disadvantage. We've got a 24-hour news cycle, which is really great, except people don't have time to think. You'll get a report published, and people will be asked for an immediate response. Sometimes there's a report being published tomorrow, we've got an advanced copy of it, what is your response? And anybody who doesn't give an immediate response can often be labelled as evasive, don't know, don't understand your subject. We've reached a stage where it's better to be first with an immediate answer rather than second with a thoughtful answer, and this needs to bear in mind when we are laying out the syllabus that we want our future astronomers to learn about based on what we've done currently and to identify the mistakes that went with it. And we're in a setup where conspiracy theories really can, really can grab people's attention. There's a famous quote that says, a lie can get halfway around the world while the truth is still putting its boots on, and we really need to be aware of that. Now, let's just go back to one thing that I'm think is very important, that we make sure that our children understand. Something may be known, but if the language is not dated, and the assumption is, well, people will understand the language hasn't been updated, for those who don't understand it. So let's look and see an example of what I'm talking about, because traditional things can be wrong, but surely everyone makes the appropriate understanding. Well, let's just have a look at that. We're all aware of sunrise and sunset. We learn about it at primary school and secondary school, and we understand what's going on. And yes, there's a typical 12-hour period. Yeah, I saw the sunrise in the east, and in the evening I saw it set in the west. And we talk about sunrise and sunset. A lot of people don't realise that there is no such thing. The sun does not rise, the sun does not set. Right. What actually happens is this. What you actually see at sunrise is the eastern horizon going down. And evening, you see the western horizon rising. And people might think that's not important, but it does lead to a misunderstanding that goes on. and it can then build on it. So we then still have to deal with, yes, flat Earth does not exist apart from in the minds of people who aren't open to thinking more about what is going on. So let's deal with just some well-known truths, and then we'll see about this. Everybody knows that the sun rises in the east and sets in the west. Or, well, okay, let's make the allowance for the fact that the horizon may be going down or may be coming up, but essentially we're talking about the sun appears to rise in the east and appears to set in the west. We all know that. We learn it at primary school, and that's got a 99.45% error about it. Only 2 days of the year does the sun rise in the east and set in the west. And yet still taught at school, the expectation being, yes, but that'll be picked up at some stage. Surely it will be. But we all know this. The far side of the moon is the dark side. We use the terms interchangeably, which is perfectly all right, apart from the fact that it's totally different things. It's coincidentally true for a full moon, and it's totally wrong for a new moon. A lot of people don't realise that. Well, one thing they do realise is, of course, that the moon rotates or orbits around the Earth. Except that's not true. The moon and the Earth orbit around their barycenter, which is 2,900 miles away from Earth's centre. But it's okay because people understand that that's wrong, except I don't think that they do. We live in a world where things being said, oh, we don't change things that work. If something works, don't change it. Don't mess about with newfangled ideas that won't work. So let's go back a little bit, shall we? And imagine this happening. So there we are, the brand new car for Fred Flintstone and co. Say, look at this, it's wonderful. Just get your family behind and push along if you need to. Listen to me. I'm telling you, it's wonderful. Look at it. Somebody says, hang on a minute, just had a thought. Wouldn't that actually help? Don't be ridiculous. That's never been needed in the past. Anyway, I can tell you why we're not going to do that. See, because with the existing model that works terribly well, if you put it on a slope, it doesn't move. If you put your newfangled idea on the slope, it runs away. Yes, we wondered about inventing perhaps a braking system. Oh, for heaven's sake, now you're just trying to invent things to deal with the shortcomings. This car with its square wheels was good enough for my father and good enough for my grandfather. It's going to be good enough for you and your children. So, having sort of laid out this idea, what are the problems with the way that astronomy is taught now? Because if we don't deal with these, they already lay problems that are existing later on. So let's deal with the first one. How do we deal with them? Well, let's deal with this one to start off with. By the way, I am not in any way suggesting that what Newton did for science was not incredibly valuable. What I am questioning is the way that we teach it. So, there's a typical class. Okay, now, sit around as boys and girls. I'm going to tell you, says the teacher, all about Isaac Newton. Newton found that things need a force to accelerate, but, and listen carefully, they don't require a force to keep moving at a constant speed. But, now what? It's really clear what's going on. Yes, but, don't argue. Isaac Newton was a very famous and important scientist. The kids are actually thinking, so if I understand what you're saying right, if I want to go from Exeter to London, all I need to do is accelerate up to 70 miles an hour and then coast for the rest of the way. To which the teacher says, as it says there, if he was here today, he would tell you how important his work is. But nobody has addressed what the kids are thinking, which is Isaac Newton was some bloke who's been dead for 300 years. And if he was around here today, his car would probably keep running out of petrol, so he'd be late for everything. Because our idea that we teach is do not overcomplicate a subject, we must make it simple. All right? Don't confuse children with telling things that are other than simple. Later on, we will deal with the additional things. So somebody says, what about, I've heard something called air resistance. We are not dealing with that until next year, chapter 7. Stop thinking, do what you're told. And it's a problem that goes on. Okay. I did some research. I did some work with NASA and brought some education things back and was dealing with children. And what we were doing afterwards, we were asking them not only what's the answer, but why do you believe the answer? So, here's a question. Children were asked, do you believe in aliens, that they exist? And if so, why do you believe it? Do you know what a significant number? Oh, most children said, yes, we believe in aliens. The astonishing thing was the reason why. There was a significant number of them who came up with a very good and compelling reason. Anyone know what that would be?
They've seen on TV.
Because Hollywood would not spend all that money on things that don't exist. It's amazing. But we still maintain this idea of keep it simple, don't complicate it, thinking that kids won't realise that in fact they're being lied to. They hope that kids will understand. Kids do understand. They understand they're being lied to. So let's look at another thing to do with Isaac Newton. This is a classic one, and exam boards still do the following problem. I've seen it in a SATS exam. What is the force that holds us to the Earth? Answer, gravity. Also, weight is a perfect answer. Now, some of you think, well, yeah, that sort of works. But if you get into the child's mind about what's going on, they do the following. Having learnt that weight is a force caused by gravity and weight is of an object is the gravitational force between the object and the Earth, to make life simple, they have been told gravity and weight are the same thing. Don't overcomplicate it. What the teacher is not saying is, you'll learn something about that later on, but I don't want you to be thinking about things that aren't at this stage. Unfortunately, this is what kids do. Well, we know that spacemen are weightless, and here's the problem. That's because there's no gravity out in space. If you presume a little bit further and say, so where's the boundary? You can say, well, aeroplanes, yeah, they've got to stay up, crash. I know what the difference is. It must be something to do with where the air runs out. So, out in space, you're weightless. Is it because you're just small? Well, no. Something as big as the International Space Station stays up in floats in space because there's no gravity. Then you pitch it to kids and say, well, what about the moon? What holds the moon in orbit? Oh, gravity does. Then they end up by saying, if you ask them, why is that? Well, the moon is big enough to have gravity, but people and the International Space Station are not big enough. We need to start telling the truth to kids to make sure that they can pick up on where we should be. I think it's perfectly acceptable to say to kids, hey, this is the first part of a story and you'll learn more of it. But there so often is, no, don't confuse them and make them think that you're telling them something that isn't complete. I think it's perfectly okay to do that. Okay. There's another thing that kids are aware of. One of those, yep. If you're going to tell kids that weight and gravity are the same thing, they know that if they go into a lift, the feeling in their stomach, and they know that if they were to stand on scales, when the lift goes down, they would see this. They don't need to be standing on weights. They know the feeling that they have. And yet they're being told, no. Weight and gravity are exactly the same thing. even though they know that when they go up, the reverse happens. Okay. This is what the teacher hopes the pupils will accommodate them with. I will tell you the truth, the whole truth, and nothing but the truth, brackets. I hope you don't notice that that's not always true. What they hope is that the kids don't view them like this. And particularly that. Okay. So, let's just look at one other thing. What's just an example? We all know about rotation of the Earth. The kids learn about the Earth rotates. There's a little animation that shows that the Earth is rotating. We tell them it spins around exactly 23 hours, 56 minutes and 4 seconds and hope that somebody doesn't spot, yes, but we've been told it's 24 hours and sometimes it's only a fractional difference, don't worry about it. We should be honest with kids. That's great because it then says, what is the problem about standing there and saying to kids, let's just imagine that I spin round once. 23 hours, 56 minutes and 4 seconds. Where does the 24 hours come in? Because we're also in orbit, and if the sun was over there, we need another 4 minutes of turn to be back to the sun. Oh, so that happens all the way. Oh, is that why this swing? Oh, right. Apparently, too often we don't do that, and we're letting kids down. So there's that. If a kid says, I've heard about this, and maybe a kid says, I've heard about that, you don't say they don't exist. You can say to them, yes, you get precession. It takes 25,788 years. It's not a huge importance at the moment. It happens, and we'll learn about that later. And should anyone say, yeah, but what about that sort of in-between spin? Say, yeah, that's really well done. You don't tell them, you're not supposed to be reading that in the book. So, yeah, and we'll come on to that later on. It's perfectly okay to tell kids everything is okay, right? So, that's got that bee out my bonnet there, but it does deal with where we're going. And we are risking with astronomy that we are going to turn kids off. Because this is what the exam used to be, the previous one, the GCSE. Okay, 4 topics. That was good. Now what's happening is they've decided we need more topics in there, which I don't have a problem with. They say, right, well, we're going to have 8 topics there. Great. Oh, and then we're going to have a second paper. 8 topics there. Total has now gone from 2 hours to 1 3/4 hours for each of those papers. So we've got to fit things in, and this is a huge problem. You see, in the past, last syllabus, you had projects that you did, and the projects counted. Kids went out and experienced, oh, hang on a minute, this isn't quite as easy as I thought. Hang on a minute, oh, I can solve it. Yeah, okay. And they get graded for it. Now, those projects are in a slightly different form. The kids have to do them. They get no credit for it whatsoever. They have to do the projects. The teacher has to assess the projects are good enough, just to make sure the teacher's not corrupt. The head has got to assess the teacher to make sure they're doing it right. And if the kids have done things that are right, they get no marks, but they're allowed to take the written exam. That is teaching kids practical astronomy doesn't count. It's just a bureaucratic nonsense that you have to get involved in. The only thing that matters are the facts. The facts, the facts. Let's just see what my time is. Yeah. Okay. One of the great things that I think is in there now panders to the kids. They love a puzzle. So, we can go back historically. Anyone any idea who he is? That's Mendeleev. And he, with others, worked together to come up with the idea of a periodic table, which was wonderful. They managed to even identify the elements that hadn't been found yet, the properties of which they could find by looking at the holes in the periodic table and looking at the properties on either side and above and below to get some idea about it. And it was great. It was a really good way of explaining the materials of the Earth. And also, what we found out in the universe. And then we came to a hiccup. Now, I think that hiccup is brilliant. So let's just have a look at it. What was discovered, as I'm sure many of you know, is that when we were looking at galaxies, there wasn't enough mass to hold galaxies together. So if they were there, they would be blowing themselves to pieces. So there had to be a solution to this. There's not enough gravity. The only thing we know about gravity is that it's associated. The key thing about gravity, I should say, is that it's associated with matter. If we've got something there which seems to be matter but doesn't seem to fit in with anything that we know about, it's great. You call it dark matter. Great. Something to do with gravity, not much of a different idea about anything else. Okay, what impact did that have? I think this is brilliant, because we were looking at saying, so was it a tiny little bit of this dark matter that we can ignore, or a bit more that we have to be aware of? Say, well, no, actually, when it came out, what we're talking about is that 20% of the universe is made of normal matter, and this dark matter seems to accommodate for 4 times as much. And if you thought that was good, then we start looking at these things. Say, okay, so faraway galaxies. Oh, hang on a minute. That one seems to be accelerating. Maybe there's a huge attractor further on, over there, that's pulling those galaxies out. Yes, so that, oh, blimey, it must be really huge if it's that big. Galaxies over there are heading off in that, it must be absolutely huge. Sorry. You ain't kidding. So when we get the maths in behind that, what do we know about it? Well, nothing in the universe happens without energy. So it must be something to do with energy. What do you know about that particular energy? Nothing. Let's call it dark energy at the moment. Now, I am aware of the fact that there are going to be some academics saying, no, that's not. We do know something about it. But if you're teaching kids at GCSE, the thing you say is, dark matter and dark energy we think exist, but we're not sure. We're not sure about this. Later on, you might be part of a group that explores this. Kids love the idea of a mystery. Because what they'll put together then is say, okay, so what have we got? We've got periodic table of normal matter. We've got dark matter. About 73% is this stuff called dark energy. What the kids love about that is, hey, they love the 3 bits of the unknown that are on there. Firstly, they love the dark matter. Secondly, they love the dark energy. And thirdly, they love whatever else is going to come next, which we don't know about yet. That's the exciting thing that we should be doing. I don't see a problem with kids having to deal with that. Okay, first of all, we thought it was 100% normal. Then it was 20 versus 80. Then it's 4.75, 22, and 73. And hopefully somebody will say that doesn't quite add up to 100%. Yeah, we're really not too sure about this at all. So let's have a look and see what really inspires young astronomers. The life, the universe, and everything is what they really are going for. So let's have a look and see. Here are a few examples. The solar system. One of the things that we've got to be careful in astronomy is not using numbers with particular suffixes that give us the idea of saying, hey, you can get your head around these numbers. The numbers are understandable. I think this actually happens with people now. We know the sun is not that far away compared with the stars. It's very easy to say the sun is not that far away. And compared to the stars, it isn't. So let's have a little look and see. What about an intercity 125? Suppose we could run that without stopping all the way to the sun. In fact, let's just make it nice about it. Anyone recognise this character?
Yeah.
Yep, good, okay. So let's put him on the train, send him off to the sun, and ask him what he thought about it when he arrives there. So when he arrives there, he says, I can tell you, so it's taken 85 years. Now, a lot of people are really astonished by that. I said, Intercity 125, I was expecting it to take several months to get to the sun. The idea is going to take close on 85 years. And then you went, oh, that's just the sun? Whoa, the sun's nearby, relatively speaking. So we look at the M42, the nebula. Diameter 24 light years. Well, that's really good. You know, take your shoes and socks off, and we're talking about all fingers and thumbs and toes and 2 legs and 2 arms. I can cope with 24, assuming that a light year makes sense. Trouble is, what's that in understandable units? Well, let's deal with the cubic mile. Kids can imagine that. Mile that way, mile that way, a mile that way. What's the volume of that nebula? In cubic miles, it's 1.4 million. Million cubic miles. Whoa, really? Okay. What about Voyager 2? Voyager 2 did some amazing work, as some of you will be aware of. It helped us to shape which theories didn't seem to work, which theories did seem to work. And 12 years to Neptune, it's a hell of a long time, but it's quite small compared with the 285,000 it's going to take to get to Sirius. M31, furthest object you can see with the naked eye. It's a long way away until you start saying, yes, but how long does it take? Oh, 2.25 million. That's 2.25 million light years. I think I can get my head around that. So you pose the question. The light you see now, where was it? What was happening on Earth when it had done 99.9% of its journey? So you can check it out, and the historians will say, oh yeah, Julius Caesar was invading Britain. And the RE teachers will be able to say, yeah, that's when Jesus was talking. And the kids say, that's incredible, the distances that are involved. So key things that I want to sort of emphasise that we're doing this is, facts is great. Thinking about it is desperately important. We need the what are the facts and why is that important? No, we just need more facts. We've also got a problem with our exam boards. I've been talking here about GCSE astronomy, and a group of ours on the Cornwall Schools Astronomy Project went to the exam boards and said, what about an AS or an A2 or an A level for kids to move into? Said, oh, it's too much of a hassle to write it. So we actually wrote the syllabus and sent it off to the exam board. I was astonished, but afterwards perhaps I shouldn't have been surprised by the answer that the exam board came back with. Far more important than whether there's a need for an A-level is that it's much more profitable if we don't offer it yet. Now, if that is not letting down the future of our kids, then there is something severely wrong. And in case you think I am overstating what our next generation can do, if they get involved in all those things, keen kids, facts, thinking about it, government and exam boards working together to give us a syllabus in our schools, we can end up with that. However, there are certain things we need to be aware of, and one of the things I wanted to do just before I finish this talk was I did want to sort of turn it round to what can we talk about the idea to illustrate that sometimes there are huge changes that come in to our science understanding if somebody is given the scope to think about it. So there's him, Max Planck. Thought he was a brilliant scientist because he wanted to prove classical physics worked, and when he found it didn't, he didn't like it, but he went with it. And I wanted to try and link between Max Planck and here what we were doing today. So, thinking back a bit, I remember the quote about the second law of thermodynamics. Right? If you're trying to do anything with it, watch out. And I came across this chap, right? Aljaz Godek, who was writing in New Scientist, which said the following: is it time to rethink thermodynamics? Because heating and cooling turn out to be fundamentally a different thing. They have found that silica will heat up and cool down in a fundamentally different way, and they know it's true, but they don't understand it yet. Oh, by the way, the link to Exeter was that a professor of astronomy here actually contributed and said the second law of thermodynamics is about possibility but not speed. She calls it the second and a half law. Somebody is posing saying, hang on a minute, let's think beyond this. It's really essential. If you think that I am sort of saying to teachers, I'm saying kids are super beings, which I think they can be if you encourage them, and I thought I would give you just a little practical thing. This actually happened to me. I go into schools, primary and secondary schools. The tiny ones are good and they offer, but they're normally asking simple questions. Secondary school children have a real problem. They've got the brains up here to talk about it and they operate self-censorship. Not, is that a good question, but what are my friends going to think of me? Perhaps I won't do it. The real ones that really get you are the 8-year-olds. Right? 8-year-olds know a lot and they're not afraid to ask. So I went to this school and I said, look, when I've done my bit, can we have a Q&A session and will you prime the kids so that I don't deal with the kids who are loud? You might know somebody who quietly asks good questions. And she said, yeah, we've got some of the children have prepared the astronomy questions. At the end, she said, I'm sorry, we're only the first child asked the question we prepared. I'm afraid the rest of them seem to ask a different one which occurred to them. And these are the first 4 questions that I got asked by these kids. So, number 1, nice one. What is the biggest planet in our solar system? Any idea what the second one was? Oh, okay, so what's the biggest planet that's not in our solar system? Third one then comes up with, is it true that time started when the Big Bang happened? This is 8-year-olds. And some of the staff at the back, we've got about 35-odd kids here. Some of them say, well, that's quite a good question. What's the answer to that? And I know with these 8-year-olds, they don't take prisoners. If you do the political answer, I'm going to answer a slightly different question. They will listen politely to you, say, is that all right? And they will say, yes. But what I want to know is... So, any idea what the next question was? Short, to the point. The kid asked this question and sat down. Sorry. What is time? And sat down. You know what I'm thinking in there? You know what I'm thinking while I'm trying to answer that? What the hell's coming next? So I think it's important that if we want our kids to do well, we have got to unleash them. We have got to allow them to be puzzled, because kids love a puzzle. I just want to finish off by saying my grandson gave me the tie that I'm wearing at the moment, which you can't probably see from there. But it's a nice picture. We live down by the sea, and there's a nice picture there of the seabirds and a lighthouse and the sea, the waves. It's the bottom bit that's interesting. You see there's that and there's that. My grandson, because and his mum, my daughter, know me. And if you can't see that, that's what it is. And that's what science and astronomy should all be about. Not what do we know, but what don't we know, and what would be a really interesting way of finding it out. Just finish with one little question for you. Anybody any idea what's the percentage, this is important to think, right? What's the percentage of people in the UK with more than the average number of legs? Any idea? Okay, it's more than 99.9%. Think about it. Thank you for listening.